Yes, so hello again, everyone. Welcome to this Priberam Machine Learning Lunch Seminars, the first of 2022. In this session, we are going to have Isabel Rio-Torto. She's a PhD candidate at the University of Porto and a researcher at INESC TEC. She's doing her PhD under the supervision of Professors Luís Teixeira and Jaime Cardoso. And she's focus is on tackling two main issues to prevent deep learning models from being deployed to the clinics. So the need for large amounts of data, labeled data, and the lack of explainability of deep learning models. And her talk today will be on this latter topic. So she will tell us about generating natural language explanations for computer vision applications so it starts in image captioning and then goes up to this very interesting topic of generating natural language explanations of classifier decisions. So please, Isabel, you can start when you're ready. And thank you again for this talk, of course.
No, thank you for inviting me and Priberam for organizing such an amazing event open to the community. It's a pleasure to be here. So let me just share my screen. Okay. Okay, so, okay. So you're seeing my screen now, right?
Yes.
Okay, and the slides, okay. So I think it's working. Let me just, yeah. Okay, so as Diogo was saying, I'm going to talk today a little bit about natural language explanations and how we can go from captions, from image captions to these explanations. Diogo already made a pretty nice introduction, but just a little bit of background. So I am a master in electrical and computers engineer at FCUP. And my master thesis was already related to explainable AI, more on the vision part. And so now that I am on my second year of my PhD, I'm working a little bit more on this connection between text and images. And so this is what this talk will be today about. So just to give you a brief outline, so I'm just going to introduce the theme a little bit. We're going to talk a little bit about what are natural language explanations, a brief, let's say, enumeration of some applications of natural language explanations for NLP. And then, yes, the main focus for me is natural language explanations for vision. I'm not at all an expert in NLP. This is my first time working with text, and I'm always interested in this connection between image and text. And then I'm just going to show you a little bit about what I call here, like our 2 cents on the matter. So the work we've been developing in this area. And then I'll just conclude and maybe start a discussion with the audience, which, by the way, I thank for being here, of course. So just a brief introduction. I don't want to go into much length about what explainable AI is. I think probably most of you know what it means. And in general terms, it has emerged as an effort to make machine learning models more understandable to humans. So we want to keep the high predictive capacities of these techniques and still try and understand a little bit why these models decide what they decide. And of course, I could talk in length about this. It is needed for debugging purposes. It can help us identify and correct biases, and it might also be needed in the near future for legal reasons. And there are several methods. There is like a myriad of methods for explainable AI and for different types of data as well. So we can have like feature-based methods, for example, here where we would have relative feature importance. These are usually harder to apply to images because we do not have, you know, explicit, or at least now with deep learning, we do not have explicit features. We also have concept-based methods, or also case-based methods, where we try to justify an example of the data set with similar examples from the data, for example. And by far the most widely known would be the saliency-based maps, in which we try to calculate or compute the pixel relevance and the influence of each pixel or each image region in the classification. But in more, let's say, recent years, natural language explanations like these ones here are also starting to become a bit more explored. And this also has to do with the fact that natural language explanations are inherently understandable by humans. So we can understand a text, and sometimes, for example, with saliency maps, it's not easy, given to their dimensionality as well, to understand what the maps are telling us. And so doing the explanation in natural language would mean it would be understandable. It has a more semantic, let's say, it has a more semantic component, and it can also be easily adapted to our target audience. So we could adapt the terminology, adapt the features. We could form a narrative, so they are a bit more flexible to our target audience. However, challenges, of course, arise, and the main problem, I would say, would be with faithfulness. And here, when we talk about faithfulness, we are talking about the alignment of the explanation with the decision-making process of the system. And so how can we ensure that our explanation is faithful to what the model is actually learning? And pretty tied with this concept is also, if we want to ensure faithfulness, how can we also measure it? It's also not clear at the moment how we can do this. And I'm not sure if you are familiar with this, but common natural language generation or natural language processing metrics, such as the BLUE score or the Meteor score, basically metrics that compare a ground truth text with some predicted text, let's say. They are unreliable, not only sometimes for image captioning or text generation, but here this is aggravated. And in fact, there are studies that show that like metrics like the blue score actually correlate fairly badly with human collected explanations. I just want here to clarify as well one thing, that when we talk about natural language explanations, we can talk about systems that learn from natural language explanations. There is some research in this topic, and here let's say the goal or the intuition is that if we learn with the explanation, we are ensuring that the label is more robust, and the prediction is actually based on the things we want to explain, on this justification. But here I'm going to focus on systems that generate natural language explanations. So hopefully not just learn with them, or not primarily learn with them, but generate the natural language explanations. This is just to clarify. As I was saying as well, I'm not at all an expert on natural language processing, but I leave you here a few references that are related to the generation of natural language explanations for NLP problems. And these are sometimes a bit different from the ones we want with vision, because with images and disconnection between images and text, the challenges are a bit different than here with, let's say, just the textual part. But well, if maybe someone in the audience is interested in this topic, here are a few works that can perhaps guide you. So the main topic I wanted to address, natural language explanations for vision. And here I want to, let's say, take a pause and really focus on the distinction between what is a caption and what is a natural language explanation. So when we have a caption, it means it is a detailed description of an image, okay? And usually or ideally, it would mention all the existing objects in the image for it to be a detailed description of that image. And so we can say that it is purely image relevant. For example, we have here a very nice representation of what I'm trying to say. So it's like we have two axes, and on one of them we have the image relevance, and then on the other one we have the class relevance. So a caption, an image description, is more concerned with the image relevance, so what is in the image. Whereas with a natural language explanation, we might only want to refer to a subset of the existing objects. So it is, here we are more concerned with the classification or with the predictive outcome. So we want an explanation for that outcome. We don't want to consider the entire image if the entire image is not needed for the prediction. And so here we need to combine not only image relevance, but also class relevance. And so a visual explanation here, sorry, just to clarify, the authors of this first work that kind of introduced this topic call this a visual explanation, which I think nowadays that we have the saliency maps might have been an unfortunate name. But what they mean here is the textual explanation that is related to the vision context. So our natural language explanation would have to combine both. So it can not only focus on what the image has, and it can also only focus on the definition for the class. And I also have here a bit of an analogy with medical reports, for example, for X-rays or for other exams. Sometimes they are divided into the findings and the impression sections. And we can kind of think, not completely, but to some degree, we can think about the findings section as the caption describing everything that is present in the image, all abnormalities and normal regions. And then the impression section could be more of the natural language explanation. So it would be like what regions or what abnormalities lead to a certain diagnosis. So I just wanted to make this clear distinction because as you will see also during the presentation, I have found that the literature sometimes is not very clear on this distinction. Yeah, so just here an example. So this is from the CUB dataset, the Caltech birds dataset, I think. And we hear this dataset has the advantage of having, let's say, everything. So the description, the caption, the class definition, so a sentence that describes the class, and then the explanation. So for example, in this first example, the description of the image could be that this is a large bird with a white neck and a black back in the water. And this class is defined, so the Western grave is a water bird with a yellow pointy beak, white neck and belly, and black back. So you see, the class definition can be more broad, and some of the attributes that are mentioned here are not present in the image. Let's say, for example, the yellow pointy beak at least is not described in that caption. And then the explanation would be that this is a Western grave because this bird has a long white neck, pointy yellow beak, and red eye. So it also makes a balance between the description and the class definition. But I will make this even more clear in another example afterwards. Yes, and you might be thinking it, at least I am, sometimes this distinction is not easy to make. So like in data sets, for example, ImageNet, that we have, for example, an image of just a dog, it's not easy to distinguish the caption, like there is a dog playing in the park, something like that, from the explanation of what a dog is. So I would say, but this is a bit philosophical yet still, that, how can I say it? That describing the dog into smaller parts, into its basic units, would be a bit hard for us. And so I don't know if these approaches or these definitions could be applied to every scenario, but in many others they can, as you also will see in a bit. So this is, I would say, the first and the seminal work on generating natural language explanations. It is the one I was referencing in the previous slide. And it was basically proposed in 2016, more or less. And it uses a compact bilinear classifier to classify the image. And not only to classify the image, but also for feature extraction. And then they use an LSTM condition on the predicted class label and on the target sentence. And here the target sentence would be an image caption, not a natural language explanation. And here, this architecture distinguishes itself from the image captioning paradigms of the time, where you just had like an image, a feature extraction network, a CNN, for example, and then an LSTM or other language model that would extract the text from the image. And here it distinguishes itself from that paradigm because we have a recurrent explanation generator that is conditioned on the class. And this is done to ensure this class relevance that I was talking about earlier. And it also has a reinforcement-based discriminative loss that basically what it tries to do is it takes the generated sentence and it uses a sentence classifier, pre-trained sentence classifier to classify the sentence. And so if it classifies the sentence correctly, ideally the sentence will have enough class discriminative information. And so it would be a valid explanation. And of course, it also has a traditional cross entropy loss to ensure that the model can generate coherent sentences and to ensure also that these sentences are image relevant. So this relevance loss here is used to train the model with the target sentences, so with the image captions, not with ground truth or human collected explanations. However, of course, one potential problem of this architecture is that it is possible for the explainer, to learn to justify a given prediction by mentioning an attribute that is frequently occurring within a class, but it can do so without even looking at the image. So it can learn to generate the sentence without looking at the image. And in order to alleviate a little bit this problem, the same authors a few years later proposed an extension of this work, and so used the same explanation generator from the previous work and used it to generate various explanations, not only one. And then they would use a rule-based attribute chunker to extract a list of attributes from the sentences. And it would be a simple process, like finding phrases that are that synthetically match some templates for example, a noun followed by a verb and an adjective, or an adjective followed by a noun, a simple matching process. And then the interesting part is that each of the extracted sets of attributes would be grounded to a region in the image using an off-the-shelf explanation grounder. And so the idea here is that this explanation grounder would give us a set of regions and scores for each attribute. And then these would be would be fed to a phrase critic, and this phrase critic basically encodes these attributes with, for example, an LSTM, and would give us a regression score of the final relevance of each explanation. And so we would choose the one with the highest score. Exactly. So here the authors try to introduce this explanation grounder to ensure that the attributes mentioned in the sentences are actually present in the input image. Yeah, so these two works would be, well, at least as far as I know it, and as far as my literature review went, were the few works that did not use ground truth explanations, human collected explanations. So their data set here had the image, the label for the classification, and then the captions, the image captions, but they did not use directly the ground truth explanations to supervise the process. And the works I'm going to show you next, if I'm not mistaken, all of them use these ground truth explanations to guide the training and to learn to generate them. So like in a traditional supervised image captioning paradigm. So we would have the image, we would have the corresponding description of the image, and we would simply use cross entropy loss, for example, to generate and to learn to generate those sentences. I'm just saying this because I'm a bit of a skeptic of these methods, but we can discuss this later. They are still, of course, very important and very meaningful for the work we are trying to do and for this talk, of course. And so also in 2018, one of the models that was proposed is this one from multimodal explanations, justifying decisions and pointing to the evidence. And this is an explanation model for visual question and answering. And you are also going to see that many applications of and many works in this area are for VQ&A tasks. And here the authors couple a multimodal explanation model to the, let's say, traditional answering model. And so they here not only obtain a textual justification, but also a visual pointing, so kind of a saliency map of where the model is looking at. And as I was saying before, so this textual justification module is trained for next word prediction with supervision from human annotated ground truth justifications. So the authors propose, if I'm not mistaken, 2 data sets, one on action recognition and one on visual questioning and answering. And so they collect human explanations given by a pool of annotators. And this is how they train their model. And also here, just note that the textual justification module gets not only the visual pointing, but also the inputs from the answer and the question as well. Another similar approach, it's an extension of the previous one, and this one ensures that the generator focuses only on explanations that are consistent with the VQ&A model. And so they first segment the image and along with the embedding of the question, they feed this to the VQ&A model that also has attention. And the main innovation of this work would be that the authors filter online the explanations according to their consistency. So they basically use GradCam. It can be considered an explainable AI method that also gives us heat maps of the relevant image regions. They are called here class activation maps, so CAM. And they filter the explanations that are not consistent with the explanation for the answer. So they basically, imagine they have two explanations in the data set. They produce the GradCam visualization for one of the explanations. So that would be the red connections here. They do the same for the other explanation, and then they do the same for the answer. And so, as you can see here, for example, the one in gray focuses more on the sea, while the other one focuses more on the surfer. And so, since the GradCam visualization of the answer also focuses more on the surface, they reject the gray explanation and maintain only the red explanation. And so this is their online filtration for ensuring faithful, what they call also faithful multimodal explanations. More recently, people alongside the research also on image captioning have moved a little bit from LSTMs and RNNs to transformers. And so this is just a brief overview of one of the methods that produces natural language rationales. Sometimes natural language explanations are also called rationales. I don't know, from what I've gathered, they are pretty much the same types of explanations, but maybe slight differences can exist. I don't think it does, but I would have to actually investigate this further. But here, so they propose the rationale VT, Vision Text Transform, and they generate explanations for or rationales for visual common sense reasoning, visual textual entailment, and also visual question and answering. And the main idea of the authors is that to obtain accurate explanations, a model needs to understand the image not only at the pixel level. So it does not only need to recognize objects, but it also needs to understand the context in the contextual content at the semantic and pragmatic level. So not only the relationship between the objects, but also the understanding the intent of the overall action represented in the image. And so what they try to do is to combine textual inputs, so the question and the ground truth answer, with inputs from different visual models. And they do this then to give these outputs of different visual models to a GPT-2 transformer. And so they combine outputs from object detection, from a grounded situation recognition model, and from a visual common sense reasoning model that is called the visual comment. I'm sorry, I think I have here. Sorry, I thought I had a question in the chat. Feel free to ask questions, I don't mind. So here they basically use these outputs of several types of visual models and then just concatenate them and put them into a GPT-2 transformer to generate the explanation. And once more, they are used to, they train this with ground truth explanations. Here, this is a more recent work that actually compares the last ones I've been telling you about. So the multimodal explanations justifying decisions and pointing to the evidence is the PUJX. Then the faithful multimodal explanations, then the rationale vision VT transformer. And then the authors also propose a new approach to this generation. And they here use a uniter transformer. I have it here, but it simply is a transformer that gets as input not only text or not only image, but region features with also the sentence as well. So it kind of blends all this information available. And here the authors basically just do that and just blend all this information together, and then these extracted embeddings are given to a GPT-2 model to generate the text. And the idea here is that these representations are a more efficient imaging representation of the image and the question as well. Yeah. But also, if you want to check this, it's also a good, let's say, review of the other methods and the comparison between them with their proposed data set and benchmark. So, sorry, let me just see if I have time. Yeah. So here I wanted to give you a brief overview of the most significant works in the area. And well, I'm not sure I agree as of now that to explain what a model is doing or is predicting, we want a model that is trained to generate the explanation we want. And so here I'm going to go a bit onto, let me just, yeah, into our proposed approach. So we are not interested in learning to generate these natural language explanations by supervising them, because we think, well, if I get a model, I get an image, and I get the corresponding text, then I'm just doing supervised captioning. So, but I call the output an explanation because a human gave me an explanation and not a description of the image. So what we try to do, or what we are trying to do, let's say, is to try to learn these natural language explanations without directly supervising them. A bit like the first works try to do here. So we're kind of going back, let's say, to the basics. And for this, and related with what I was telling you about before, that common data sets like ImageNet, for example, might sometimes be hard to distinguish clearly what is a caption and what is an explanation, because we sometimes don't know how to subdivide certain concepts, like the concept of a dog, for example. What we tried to do first was to create a simple example, a really toy data set, where we would have this clear distinction, so that we could then evaluate more objectively if our system was producing an explanation with class discriminative information, or if it was only, let's say, producing a caption. And so we created this really simple data set. And so we said that we would label the images as negative if there would be no triangles on the left of the leftmost square. And it would be positive if there would be at least one triangle on the left of the leftmost square. And so our idea here is that when we want a caption, we want to describe all polygons present and their relationship. For example, here there are 4 figures, the colors of the figures as well, and the green triangle and the blue square are in the middle of the orange square and the purple triangle, so they're relations. But our natural language explanation would be ideally, let's call it a subset of the objects, because here we are only, when we want to, in order for us to classify an image, we just need to get or to identify the leftmost square and the objects on its left. And so here we wanted a clear distinction between the two. And having this data with us, what we did was we proposed an architecture that is based on an encoder-decoder transformer. And it has as an encoder a vision transformer. So it gets as an input the image, and it outputs not only a textual explanation or a sentence, and then it uses both the embeddings of the image and the text to classify. And what we tried to do first, in a first training stage, was to just train the encoder and the decoder to be able to do image captioning. So we would get the image and we would output the caption. And we did this to train not only the encoder to learn to perform feature extraction, but also for our language model to be able to generate coherent sentences for our domain. And then in a second stage, the idea is that if we are using the explanation to influence the classification, when our classification loss is updated, it will also backpropagate and update the textual sentence accordingly to the classification. And so through this, the idea was that we could ensure not only image relevance by, of course, extracting the features from the image and using them to classify, but also to ensure this class relevance by altering the explanation accordingly to the classification. We also thought about other alternatives for the first training stage. We, of course, started with, let's say, the more easy to train, and that would be supervised image captioning. And then we thought about just training these two blocks with contrastive learning, or even separately with self-supervised learning, for example, masked language modeling and techniques like that. But for now, we only did supervised image captioning. And well, in the first training stage, of course, the data set is quite simple, so we obtained fairly good results in terms of the usual NLG metrics. So our language model is fairly capable of producing the text. And then in the second training stage, we see that we could obtain with the various approaches good accuracies. And just to give you a bit of context, what we did also was a bit of I could call it dropout, but a bit of randomization in the training process. And so sometimes we only gave to classify, we only gave the text, sometimes we only gave the image, and sometimes we only gave the two with different probabilities. And so that is what you see here. For example, this first is just with the text, and then the last one is with every of the three possibilities with equal probability. And this was the one that achieved the best results when comparing the produced explanations with the ground truth explanations. So here, of course, we use our ground truth explanations, but just to measure or to try to obtain a more objective measure of how good or how faithful they are. And I just present you here a few examples. And as you can see, the results are not quite where we wanted them to be yet, because what we found out was that, okay, the network was good at classifying, it was good at captioning, but when it starts to change the captions and to adapt them to the classification, you can see that there are mistakes here highlighted in red. And there are also a recurrence of some sentences. For example, the brown triangle is on the left of the square, and there isn't even a brown triangle here. And so for the positive instances, this sentence, for example, kept reoccurring. And this is in fact the problem that the authors of one of the first papers I was showing you found out, that the explainer is can produce a valid explanation without even looking at the image. So we here, when we tweaked the captions in the second phase, we lost the image relevance. And so this is the current stage of this project. We are thinking about a few ideas on how to tackle this, maybe even include an explanation grounder like previous works did. We are also thinking about including here a cyclic step. So ensuring that with the generated sentence, we can then try and generate parts or the most important parts of the original image, so that we would really oblige that sentence to contain relevant image features. So this is mainly what I wanted to show you. And just to finish, so I just wanted to give you a brief overview on natural language explanation generation. And these can be a good alternative to other explainable AI methods. They can complement other explainable AI methods, and mainly because they are inherently understandable by humans. As you saw, the majority of the works follow this kind of supervised image captioning paradigm. And well, that's just my, let's say, personal opinion at the moment. Maybe you can change my mind, I don't know. But ideally, if we want to explain what the model is learning while classifying, we should not be teaching or influencing the model to generate a given text, because then we would be doing captioning and not explaining the classification. But that's just my current opinion, let's say. But of course, there are many challenges still ahead. The ones I talked about a little bit, to ensure the faithfulness of the explanations, and how can we ensure this if we don't have a metric for the explanation quality, and also how can we tackle this inherent subjectivity of the matter. But well, I just leave you here with some food for thought, and maybe we can discuss this aspect. So if we teach the model to generate these ground truth explanations, are we truly explaining the prediction of the model? And would it even be possible to do this generation without this supervision? I don't know. What do you think? Well, for me, is all for now. I hope you enjoyed the talk. You had a little bit of an introduction to the topic. And once more, thank you for having me. Thank you for listening, and please be free to ask any questions.
Thank you, Isabel, for this very nice talk. I guess we still have a few minutes for questions. You can ask them directly, or if you prefer, you can make them through the chat and I will read them. So let's see. Well, while people are still thinking about their questions, maybe I can start with one. So Isabel, you showed us the results of your model in generating explanations for this toy data set that you have built, but I wonder, what is the actual classification accuracy of the model? Because, well, there you are using a vision transformer, which is well, actually, I have two questions. So if the first is, what is the classification accuracy there? And if you have tried, instead of using a vision transformer, with a CNN, because I wonder if a CNN could learn this kind of spatial relative positions of two objects, I think it's not very easy for a CNN to learn. So yeah, these are my two questions about it.
Yeah, so regarding the first question, I don't know if you can see very well here, but when we try with just the image, we get also very good accuracy. So the classification problem is not a difficult problem. And it was also not our main goal to make it too difficult for now. Yes, we have not tested with the CNN, and we are aware that CNNs are not very good at finding out relationships between objects. Maybe we could try and see what CNN would do here. I'm pretty sure it would also influence the generated sentences as well. Yeah, and I'm also not sure if it would still lose this image relevance I was talking about, but it could be an interesting point to try. Well, yeah, I just went for the transformer because in terms of implementation at the moment I was doing it, it was easier to do it in the framework, but yeah, maybe I will try with the CNN here.
Yes, I think that with the CNN, the classification accuracy would not
be so good.
Yeah, yeah, but it would be interesting to evaluate. So I guess we have we have a question in the chat. So Katarina Blanc is asking you what causal mask language model you are using after the vision encoder, so the vision transformer.
Oh yeah, I completely, sorry Katarina, I completely forgot to tell you guys, and thank you Rita for answering. I have it here. So we tried with some GPT-2 pre-trained models and BERT as well. So I don't know if you're familiar with it, but in the Hugging Face Transformers library, you can use the weights of a decoder model or of an encoder model and put it into a decoder architecture as well. So that's what we did here with BERT. It's traditionally an encoder-based transformer, and we use those weights to put it in the decoder-based architecture. And what we saw was that I did not discuss this very much. I didn't want to lose track of time, but what we saw here was that with the GPT-2, since it is trained for open-ended, for open text generation, what we saw here was that it was not learning to stop the generation, while with BERT, the captions actually stopped. With GPT-2, like the first sentences would be correct for our captions, and then it would just keep on generating. I'm not sure here if we would need more data to force it to learn this, to stop this generation. But with BERT, we obtained it like more off the shelf, let's say. And thank you for your questions, and Rita for helping.
So Katrina added one extra comment in the chat. So she says that there has been some work where it was shown that GPT's reasoning ability in arithmetic could be explained by a high frequency of the different numbers in the training data set. So she's wondering if your models can also be prone to this. So for example, when you're fine-tuning in your data set, like having higher prominence of some colors or some figures. So I think that, yeah, so please answer, Isabel. Isn't the question not to me, it's to you. So
no, but you can also give your thoughts.
No, but you first, please.
No, but yeah, I'm thinking that it will probably happen. We tried to balance the data when we generated it. So I don't know if the prominence of the figures would happen. I think they are fairly balanced. But the colors, well, we also tried to balance it, but maybe the colors could influence. The colors are just here now because we wanted to see if the explanation could be really specific on the polygon. Because even now when we have the brown triangle is on the left of the square, in a previous version where we did not have the colors, it would give us the triangle is on the left of the square. And so we would not know specifically which one of the objects it would be. And we are really interested in the specific objects to validate the approach. But well, thank you, Katarina, for your comment. I will have to check that work. I am not familiar with it, but I will be sure to check it and to really see if it happens here or not. The errors, well, thank you. I appreciate it if you can share it. Yeah, I don't know if the errors could be explained by that. Our main suspicion now is that the classification loss is altering too much the explanations, and they are in fact losing, as I said, their image relevance. But that is definitely a very interesting point to look at. Thank you. Diogo, I don't know if you want to.
Yeah, what
further
I was
comment.
going to add, but I think that it has somehow been covered by your comments, is that probably you are aware of this and you have taken precautions with regards to that, but you should be so you should make sure that there are no spurious correlations between your in your data set that could also allow you to predict the correct label. For instance, there might be other rules other than those that you have defined for deciding whether an image is positive or negative that could also be correlated with the labels, and then the model could be also be basing its decisions on those rules. So maybe looking at the data generating process could also help, but probably you have done it when you have generated the data set. So
yeah, we tried.
One interesting thing is that even in the captions, which are pretty good, the model tends not to figure out correctly whether the square is on the right or on the left.
Yeah, that can be related to the nature of the problem, as you were saying. Yeah. Well, we also could think about other tasks where this distinction between caption and explanation would be really clear. But so far, it has not occurred to us. But maybe I can think a little bit more about that so that we do not depend so much on these spatial relations.
Yeah. I think Rita added another comment in the chat. Maybe you can read it and add your thoughts on it, Isabel.
Yeah, I really like this talk. Thank you. Yeah, when I tried BERT instead of GPT for Coco, I actually had worse results since it's not a pre-trained autoregressive model, even with that code debugging faced with cross-attention layers and training autoregressively. Interesting to see that it works for this data set. Yeah, I'm not sure. I also thought my initial experiments were with GPT as well, because of it being trained autoregressively and not with a masked language model objective. But in fact, here it's what worked. I'm not sure if it's also because we used it directly to classify, but still in this first phase, it's what gave us the best results. Thank you, Katarina, for the link. Let me just save it here.
We have one more question.
Yeah.
Rita. So
I am wondering why the side
it's so low near 0, but the spice is actually not low in slide 17.
Yeah. So here I may be a bit at fault. I don't know, because I'm really not an expert on these metrics. But we just use the traditional MS Coco cap script for evaluating. Yeah, I was also shocked to see the side error was so low, but I'm not sure why. Is it the side error metric that uses like a corpus? I think maybe that could be it. I'm not sure. I remember. Yeah. Yeah, exactly. I was not sure if it was this metric yet, but I remember reading about it, that for small data sets or for small batches, it gives a side error of 0. Yeah, I will definitely have to check it again. Yeah, but I saw that with large data sets like Cocoa Captions and stuff, it did not happen. But maybe I will need to increase the corpus as well, so that the side error does not give me such low scores. And it's the only one that is a bit it's different from the others. Let me just see. Yeah, but here it kind of happened as well. Well, thank you, Rita, for all your comments. These will be very useful for my next steps in trying to improve the work now.
So maybe we have time for one final question, if there is one, or otherwise we just finish since it's 2 o'clock right now. Let's see if someone has any further questions. So it looks like that's all. So thank you very much, Isabel, again for this very nice talk. And we'll be back in 2 weeks with another session of Priberam machine learning lunch seminars. So please join us and have a nice day. Thank you again, Isabel.
Thank you for